Friends, welcome to my YouTube channel. Dhanesh here. In this video, I am going to discuss about transfer learning. See, transfer learning is an important concept in machine learning and artificial intelligence nowadays. We use transfer learning in computer vision, natural language processing. These are all the areas we use transfer learning. You know, we humans have an inherent ability to transfer knowledge across tasks. For example, if you know a mathematics, you can use that knowledge in physics, because physics you need a lot of mathematics. If you know math and statistics, you can use that knowledge across machine learning and artificial intelligence. But in conventional machine learning and deep learning algorithms, we are not using this. They are isolated. They work in isolation. Conventional machine learning and deep learning algorithms. So how this transfer learning? It is, how we can use this techniques in our deep learning, in our machine learning and artificial intelligence. That's what we are going to discuss here. For example, if you have a data set 1, this is your data set. This is the first data set. This is the data set 1, and you have a learning system here. See, you have a learning system. This is your learning system. This is it is doing the task. Let the task be 1. This is the first task it's doing. And you have the second data set here. This is the second data set. And you have another learning system here. And it is doing the second task 2. It is doing another task. For example, you can tell to identify images, or any task you can assume. So let me keep it like this. See, it would be like this. This is here. This is task 2. This is the task 2. So what we are trying to do here, see, why can't we use the knowledge acquired by this first task, and why can't we leverage it in the second one? So that's what we are going to see. This knowledge, that is transfer learning. This knowledge we are using in the task 2. This knowledge acquired by the task 1, we are using it in task 2. This is the process of transfer learning. So you have the first data set, here you have the second data set, and here this learning system is doing the task 1 and this learning system is doing a task 2. Then why can't we, the knowledge acquired by the task 1, the first learning system, can be used in the second for the task 2? That's all about the transfer learning. This is the fundamental concept of transfer learning. Now, as we discussed, the traditional machine learning algorithms are isolated, but in transfer learning you can leverage knowledge. Knowledge means the features, weights, biases, etc. The knowledge means, when we talk about knowledge, it consists of the features, weights and biases. So these are all the things we reuse. From in transfer learning, you can leverage this knowledge like features, weights, and biases from previously trained models to for you can use these features to from previously trained models to train newer models, and even tackle problems like having less data for newer tasks. So that also you can do. See, in transfer learning, you can leverage knowledge like features, weights, and biases from previously trained models for training newer models, and even tackle problems like having less data for newer tasks. So this is the advantage of transfer learning. Now I will tell you some of the important concepts we are going to use here. See, some concepts what is a feature. See, I was already talking about weights and biases. See, weights and biases in neural network, mx plus c. Here m, this is the simplest explanation. M denotes the weight and c denotes the bias. And in a neural network perspective also, that features means a feature is an individual measurable property or characteristics of a phenomenon being observed. That's a feature. It's a measurable property. That is a feature. And another important term you need to understand here is we are going to use here is the feature space. Another term you need to understand here is the feature. So feature, I told you. Now I am going to tell you what is a feature space. So a feature is an individual measurable property or characteristics of a phenomenon that's being observed. That is a feature. Feature space means when you are given some data, a feature space is just the set of all possible values for a chosen set of features from that data. That we call it as the feature space. It is the set of the features. We can tell you are given with some data, then a feature space is just the set of all possible values for a given set of features from the data. That we call it as the feature space, because in math you learn relations and functions, then you may be familiar with relations and functions, sets. If you learn these these chapters in math, you will be familiar with these sets, relations, and functions. So this is feature space. And one more point I want to tell you is, now we are coming back to the mathematics of transfer learning. So I have given you some idea about what is the concept behind this transfer learning. Now the mathematics of transfer learning. Math behind math of transfer learning. For that, let's have a domain D. So we are defining a domain. See, domain is another concept in sets. That is in mathematics. Domain means all the x values, we call it as domain. All the y values, we call it as range. See, for example, when you write y is equal to f of x, or x is an independent variable and y is a dependent variable, all the set, all the collection of these independent variables, we call it as domain. This is domain. All the values of x, all the values of y, the dependent variable, we call it as the range. So we are going to use this domain, this term we are going to use here. So you please understand what's a domain. Now again, what I am going to tell you here is, let us assume, we are defining a domain D. So we have a domain D, and it is defined as two element tuple. So it's a tuple tuple, you know, in Python and even in math you define tuple. It's just sequence of, you know, elements. That is a tuple, and it consists of, you know, a feature space. Feature space, I already told you, it consists of a feature space. Feature space is denoted by the letter, it consists of feature space psi. This is the letter psi, and the marginal probability px. See, this tuple we defined as it contains two elements. The domain D we are defining as a tuple consisting of two elements. One is the feature space psi and the marginal probability p of x. It is the marginal probability p of x. This we are defining as the domain. So what is x? X here, I can tell you what is this psi here. Psi is the feature space. And what is px here? Px is the marginal probability, and x is a sample data point. And what is x here? X is a sample data point from our feature space. So x is a sample data point from our feature space. So this is the definition for the domain. So domain is a tuple which consists of, you know, the feature space psi and the marginal probability p of x, where x is the sample data point from our feature space. So x, you can write it as, again, you understood this. So x, I can write it as x is equal to, here, x is equal to, x and psi are different. Psi I have written as this. Psi is the feature space, and p of x is this is x and this is psi. Psi is a Greek letter, and x is equal to, you can write it as x1 comma x2 etc xn. This is x, and this xi, generally xi is an element of our feature space psi x. So this I will write it clearly. Psi, it is, this is psi. This is psi. So xi, this is element of, you know, this this we call it as the element of in sets, relations and functions. It is an element of psi xi. So this is what you need to understand. So once again, I am defining domain D as a tuple of feature space psi and the marginal probability p of x, where x is a, you know, sample data point, and which is an element of psi. And one more thing I need to understand, I need to tell you what is marginal probability. So you may be familiar with marginal probability, conditional probability and joint probability. These are the three types of probabilities. They are, interrelated. So marginal probability is the probability of an event irrespective of the outcome of another variable. That is marginal probability. Marginal probability is the probability of an event irrespective of the outcome of another variable. Conditional probability is the probability of one event occurring in the presence of a second event. Conditional probability we usually use with dependent events. So you may be familiar with those aspects. So now I am getting into I am continuing with the mathematics of, the transfer learning. So this is the way we defined, domain. So how we can use this concept of domain, to our transfer learning. Our transfer learning, we are reusing task across machine learning applications. So one application, how we can reuse the task done by one machine learning system to another one. So how we can use this in the same way, a task T, we have a task T can be defined as two-element tuple. We define domain as a two-element tuple. In the same way, the task T can be defined as a two-element tuple of the label space Y and the objective function or cost function. You know, objective function or cost function or loss function all defines the same. So how we are defining? See, the task T is we are defining as a two-element tuple of label space Y. So it is equal to, it is a two-element tuple of label space Y. You know, feature space, it is with the X variables. Label means, it's the output variables Y. So a label space Y and the cost function or the objective function eta. This is the way. So we are using the concept of domain from statistics to task. So in transfer learning, we are using it. See, this can be written as, it is the Y is the label space, Y comma, what is the objective function or cost function? You know, it denotes the error. So it is the conditional probability of Y of X. So this is the task. So the task can be defined as a two-element tuple, with objective function eta and the label space Y. And again, you can understand Y is equal to Y1 comma Y2 etc. up to Yn, and Y I is an element of Y. This is the but this is the concept here. So Y is equal to Y1 comma Y2 up to Yn, and Yi is an element of the label space. So here label space is Y is the label space, and the objective function is eta. And in here again, you can write it as, see, you understood right? See, this is here you can write it as Y is the label space. Here Y is the label space, and eta is the cost function or objective function. So these things you understood, or in a simpler way you can write it as, this is you from the earlier discussions, what you understood is Xi is element of the psi. Psi is the feature space, and Yi is the element of Y. Y is the label space. This is the feature space. This is the label space. You understood this. And we can write it as, again you can write it as, this, you can understand eta of Xi is equal to Yi. This is the simplest equation, like you can compare with Y is equal to mx plus c. Here c is not present. That's all. So this is this you understood. So from this we can come to the conclusion. From this mathematical equations we can conclude, like, given a source domain ds and a corresponding source task ts, as well as, so you have the source and the target. In the case of transfer learning, you have a source domain. From that source domain, we are transferring knowledge to the target domain. And we have a source task and you have a target task as well. So ds is the, here you have ds, it is the source domain, and you have ts, which is the source task, and you have the target domain, dt is the target domain, and you have the target task. This is the target task. This is the target domain. If ds, ts, dt and tt are the source domains, then the source task, target domain and target task respectively, then the objective of transfer learning is to enable us to learn the target conditional probability distribution in dt with the information gained from ds and ts. So the objective, this is the most important definition for transfer learning. So you understood what is ds, what is ts, what is tt and what is dt. Then the objective of transfer learning is to enable us to learn the target conditional probability distribution. That is the target conditional probability distribution, that is p of yt with respect to xt. In the target domain, we need to understand about this conditional probability in dt in the target domain with the information gained from ds and ts. So we are gaining information from ds and ts, and we need to understand, we need to learn the target conditional probability distribution, that is p of yt with respect to xt in dt with the information gained from ds and ts, where you need to understand here ds is not equal to dt and ts is not equal to tt. So this is the ideal definition for transfer learning. So you have a source domain ds and the source task ts and target domain dt and target task tt. Then the objective of transfer learning is to enable us to learn the target conditional probability p of yt with respect to xt in dt in the target domain with the information gained from ds and ts, source domain and the source task. Based on this information, how we can understand p of yt and xt, that is p of yt with respect to xt. Here the condition is ds is not equal to dt and ts is not equal to tt. So these are all the important, this is an important definition, you need to understand. And now some important points you need to understand here is, so this is the mathematics of, transfer learning. Now I have to tell you, see what you need to transfer. In transfer learning, there are some important points you need to understand, then it would be easy. Otherwise it becomes very complex and not useful as well. It would create a lot of problems. So you need to understand what to transfer. So in transfer learning, this is very important: what to transfer, when to transfer, and how to transfer. This is really important. If you are not doing this correctly, it will create more problems than it is it's helping the things. So you need to understand. So the transfer learning makes sense when task A and task B have the same input X. This is very important. First point, the transfer learning makes sense when the task A and task B have the same input X, same X. That's very important. The second point you need to understand, you have a lot more data for task A than task B. More data with task A. This is very important. So you have lot more data for task A than task B. Then the third point is Low-level features from A could be helpful for learning B. Low-level features from A could be helpful for learning B. So these 3 points you need to understand. The most important point here is 2 points are task A and task B have the same input X, and you have a lot more data for task A than task B. So these points are very important when you talk about what to transfer, when to transfer, and how to transfer. Now, what are all the different scenarios, as different conditions comes. So next I am going to discuss about the different cases. So the first thing is the first case is, you can write it as, this is one case, psi of x, psi, the feature space not equal to the psi of t, the source and t, the feature space of source and target domain are different. So then this is the first case you can come across. If we talk about an example in the context of natural language processing, if the documents are written in 2 different languages, see, this is an example in the context of natural language processing. If the documents are written in 2 different languages, then this is the case. Then I am getting into the second case. So now this is the first case. Now the second scenario you can understand here is the second one. The marginal probability P of this is not psi, sorry, this is x, P of x, yes, not equal to P of, this is x, not psi, P of xs not equal to xt. That is the marginal probability distribution of source and target domain are different. That is, the second case, the marginal probability distribution of source and target domain are different. If you need, an example for this, again in the context of NLP, if the documents discuss different topics. From the context of NLP, I can tell you an example. If the documents discuss different topics, that's an example. Then the third case, it is the third scenario. It is this is the third case. There, ys not equal to yt. The label space between the task are different. The label space between 2 tasks are different. That is the third case. The label space between 2 tasks are different. If you want an example, the document need to be assigned different labels in the target task. That is an example from the context of NLP. The documents need to be assigned different labels in the target task, and this is a very rare case. That is the third one. Then the fourth case, you will come across in transfer learning is, this is the fourth one. The conditional probability y of s with respect to xs not equal to the conditional probability of y of t with respect to xt. This is the fourth case. That is, the conditional probability distribution of source and target tasks are different. If you want to, if you need an example from the NLP context, the source and target documents are unbalanced with regard to their classes. So that's the example. The source and target documents are unbalanced with regard to their classes. So this is the different cases, different scenarios you can come across in transfer learning. Now I am getting into the transfer learning strategies. So next is the last part. It is the different transfer learning strategies you can use. So there are three types of transfer learning strategies we usually use. One is the inductive transfer learning. First one is inductive transfer learning. In this case, the source and target domains are the same. In inductive transfer learning, the source and target domains are the same, yet the source and target tasks are different from each other. Multitask learning is an important area where we use inductive transfer learning. You may be heard of multitask learning. So this is an important area where we use inductive transfer learning. Here the task can be regression and classification. So normally we use that task like regression and classification. These are all here the task can be regression and classification. So this is about inductive transfer learning. This is a transfer learning strategy. The next one we can discuss is the next transfer learning strategy we use is unsupervised transfer learning strategy. It is similar to inductive transfer learning. This unsupervised transfer learning is somewhat similar to inductive transfer learning with a focus on unsupervised tasks in the target domain. With a focus on unsupervised tasks in the target domain, here the task can be clustering and dimensionality reduction. Here the task we use are clustering and dimensionality reduction. You may be familiar with this. Next is the third strategy we use is transductive transfer learning. The third one, it is transductive transfer learning. Transductive, TRANS, transductive transfer learning. Here there is a similarities. Here there is similarities between source and target tasks, but corresponding domains are different. So this is the case. Here there is similarities between source and target tasks. Tasks are same, but corresponding domains are different. Domain adaptation, sample selection bias, covariance shift are important areas where we use transductive transfer learning. So in transductive transfer learning, there is similarities between source and target tasks, but corresponding domains are different. Domain adaptation, sample selection bias, covariance shift are important areas where we use transductive transfer learning. So this is all about transfer learning. Thanks for watching.